Express apologies for being slightly off topic, because this doesn't, it may be kind of geometric and kind of combinatorial, but it's not really representation theory unless I sneak in the fact that the K-theory, equivariant K-theory of a point is a representation ring, but that's, you know, I'm never going to, so I'm a little bit off topic, so, well, you'll have to deal with it, I guess. So, thankfully, I guess I think Naito defined the affine Grassmannian for us, but let's just remember. Oh, sorry. That's the title, and this is joint with Thomas Lamb and Anna Schilling. So let G be a semi-simple algebraic group over the complexes, and T a maximal algebraic torus, and I put that in for later. Let's let O be the power series over complexes, K the Laurent series, and the affine Grassmannian for G will be the G of K mod G of O, and this is the in variety. Now, for certain reasons, I may need to go between the usual these in varieties and in flags and stuff like that, and other kinds of flags, and hopefully I won't be too sloppy about that, since some experts like Kashiwara are in the audience and will notice when I make such a mistake. So what are we? Okay, so this space here. This is almost a Kac-Moody G, and this is almost Kac-Moody maximal parabolic, almost up to some central extension that doesn't matter when you mod out. And so this thing will have Schubert calculus. You can do Schubert calculus with this, and so Peterson, in a very amazing unpublished work, as he likes to do, proved some really amazing stuff about this Schubert calculus. So I'm going to put lower subscripts for equivariant homology and upper subscript for equivariant cohomology. So lower so I'll never actually write down H sub I or H sub 2I. So I'll just put the group down there. So Peterson showed that there's a Hopf. Well, first of all, there's an algebra structure on the equivariant homology. I'm not going to discuss this because I'm going to tell you how to get it for the K theory. But these two are dual Hopf algebras over the equivariant cohomology of point, and the really cool thing. So he did several things. He realized this equivariant homology as inside the graded Nil-Hecke ring of Kostin and Kumar. Actually, a slight variant of it, and I'll point out the subtleties in the K-theoretic setting. So he did this and characterized the image of Schubert class and then proved this amazing theorem, which is his punchline was that if you take this equivariant homology and localize at some stuff, you get an isomorphism with the equivariant quantum cohomology of the finite flags localized at quantum parameters. and this happens in such a way that the Schubert classes here go to Schubert classes here. So what this says is that the quantum equivariant quantum Schubert calculus for flags, which includes the ordinary quantum cohomology and the ordinary cohomology, is contained. You can get all the information from over here. Furthermore, there's no restriction. There's no reason why you can't. You can also do all of these finite dimensional homogeneous spaces. G mod P. You just have to. Localize at a different set of things and then take mod out by an ideal. Yeah.
Is it really P or is it equal?
No. This G is this G is the usual one. This is like this GK is close to the GF. It's the finite dimensional one. So this is a huge theorem, and in his notes he has an algebraic track of proof that goes this way and a geometric track that goes this way. And they don't quite get to the proof. So Thomas Lamb and I went through the exercise of pushing through an algebraic proof and writing it down for posterity. But
G mod B or Grassmannian? Somehow it's confusing. How are you labeling the Schuberts on each side?
Okay, so what happens here roughly is that these things are like translations that are getting elements that are getting inverted here, those sorts of things. And so if you think about losing those, then you have the same amount of stuff on both sides. Here you just lose the quantum parameters. Now when you go to G mod P, then as I said, you have to localize different stuff, so, sort of like translations for. Well, I don't want to explain the details because but here you're killing stuff, so you have to kill some stuff for things to match up. But you get all of these quantum cohomologies, equivariant ones. So this is an amazing theorem. So furthermore, Thomas Lamb showed that he found an algebraic way to lose the equivariance. And so he can compute in the Nil-Coxeter algebra, and this computation, if you calculate things far enough, you actually get combinatorial formulas for everything. So if you worked, the moral is that if you worked hard enough in working inside this Nil-Heck algebra, you could get all these Littlewood-Richardson kinds of structure constants you want. By using these characterizations, but those computations are kind of hard. But in principle, you could do that. So our goal is to do the analog of this to K-theory. Unfortunately, we can't do this part. But I have some philosophical reasons why I think that this part can't work as well as it did here. Something should work in K-theory, but not anything nearly as good. Nothing. I would be really surprised if something like that were true. So that's what we're up to today. Okay. So over here, I think I'm going to put a kind of thing. So the first set of things I'm going to do is going to work in Kac-Moody generality. So it's like, okay, it's so general as to almost be I don't know, not quite as fun for me. And then we'll get more specific, get to the affine case, and then to the Grassmannian case where cooler and cooler things happen because you're getting in a more special situation. So we're just going to work with Kac-Moody flags. So X will be Kashiwara, or thick is a nice word for them, Kac-Moody flags. So for technical reasons, we want to work in this kind of flag manifold. you can think this is like a G mod B minus. This isn't a group, but it's you can think this is the Kac-Moody group, and this is an opposite Borel, and your Schubert cells. So for element of the Weil group, your Schubert cells are something like this. These things are honest cells, although they're infinite dimensional. They're like this. They're like the speck of a polynomial ring with infinitely many variables, but they are honest cells, and they're closures. These are Schubert varieties, and they have the property that if the closure of the vth one contains the wth one, if and only if v is less than or equal to w in Bruchau order. So this is sort of the backwards of the what you may be used to. On the other hand, when you compute the localizations at torus fixed points, you find that this is the right one. And also you realize why Kostin and Kumar had so much technical issues in their paper. Yeah, so those are the Schubert varieties, and these are finite codimensional. So the codimension of xw is the length of w. So the cell for the identity is dense. It's a big, gigantic cell, and then in its closure you get these other strata, and things get more and more singular as you work your way further into the closure. So that's the way things look. And so what I wanted to define was what the equivariant K-theory is. So so let S be a downwardly closed, a Bruchau closed subset. So if something is in S, then everything below it is also in S, and we just define this open set that the translates of the big cell by Weil group elements in this downwardly closed subset, or order ideal, whatever you want to call it. This is also the union, disjoint union of the Schubert cells. And this is finite. And so you just got this finite union of cells, so it makes perfect sense to talk about coherent sheaves on such an open set. There's no issues, and so you can define the B-equivariant K-theory of this on this open set to be the Grothendieck group of B-equivariant sheaves on this open set. So you may be weirded out by the fact that it's like your base ring has infinitely many variables, so like it's very non-Noetherian. But you should think that the resolutions stop in the usual kind of way, and so that you don't have any problems in this situation. And then you define the equivariant K-theory of the whole thick Kac-Moody flags to be the inverse limit of these things. This is this KB thing is a contravariant functor. Okay, so and when you do this, you get that so the structure sheaf of a Schubert variety is one of these kinds of things if S is big enough, and then these structure sheaves form a basis. Maybe I should put B here really, but it's the same thing. S2. So, but this is a this is not this is a product, not a sum. So if you try to expand a class, you might go on expanding forever. Like it happens when you multiply two K-theory Schubert classes and you expand the answer in Schubert classes, it might go on forever. That's kind of a fun kind of thing that didn't happen to me before I did calculations in this situation. Okay, okay, that's fine, but that's not very hands-on, and I like to compute things. So the algebraic replacement is as follows. So and nowadays, this is people call this this kind of simplification so GKM theory. So even though in this case it was known to Kostin and Kumar, the moral of this story is that if you have some kind of space with a nice enough torus action, so maybe it has isolated fixed points and finally many stable curves connecting those points, then you can reduce something like equivariant cohomology K theory to a combinatorial problem. So reduce computations and to combinatorics, and for people like me who want to compute things, this is a happy thing. So I don't have to be scared of this geometry. I can just compute away in a different way. And the way this works is that the Val group, or the points inside the flags that corresponding to the Val group are the torus fixed points, and these are included into the whole the whole space. And so if you let I sub w be the inclusion of a point into X with the image w, then you can we'll localize. So I'm going to switch to torus equivariance here. And this is a discrete set of points, so it's just a bunch of copies of K theory of a point. And so that's the same thing as functions, just ordinary functions. This last thing is just functions from this fixed point set, where I'm now going to replace that with the Val group to equivariant K theory of point. And this thing is just the representation ring of T. So that's just formal, or if you want, the group algebra of the weight lattice. So that's where where characters live. So this is not a mysterious thing. And so in GCAM theory says that there's an injection, a ring injection, actually algebra. So everything works over the equivariant K theory of a point, and the image. So a function f is in the image. I should tell you what this does. It sends a class to the function, which sends w to the localization of that class to that fixed point. And f is in the image of this localization map, if and only if a certain divisibility property happens. So if it's always the case that f of w and f of a reflection on w differ by a multiple of 1 minus e to the alpha, this is for all positive real roots, alpha and w Val group element. So this is known to Kostin and Kumar, and And you can compute with these things. So if we take the Schubert class and you send it under loc to we'll just call the function psi v. This function you can compute it explicitly using a divided difference recurrence, and I have it on my computer. I can do it. Just put in a generalized Cartan matrix and compute the values of this. So it's all very friendly from computation, and as long as you can compute as far as you want. Okay. So that's a very happy world. Now I want my dual pair of Hopf algebras, and so this is sort of like one side of things. Now I need the dual side, and so I need something of the same size but sort of dual to it, and so the replacement. Now, what I should really have is something like this. What I should really do is define some kind of perfect pairing between the thing I just defined and something else which I haven't defined, and then work in some kind of duality using some sort of intersection, equivariant intersection pairing. But we're just going to work algebraically. So whatever this should have been geometrically, okay, there should be something over here, but okay, I'm going to replace it by something algebraic. So they're going to replace this with something algebraic. And this idea is also due to Kosten and Kumar. So the Nilheke ring. This is Kosten and Kumar. And so it's defined as follows. So so let Q of t be the, first I'll define a sloppy version, and then I'll define an integral form of it that's the correct ring. It's just easier to write this way. So let's take the representation ring, which is the same thing as the equivalent K theory of a point, and take the fraction field, Q of t, and then the sloppy form of the Nilheke ring, the one with the bad denominators, is just the smash product of rational numbers, group algebra of W, smash with these field elements. Now see, the action is just that W acts on T, and therefore acts on the representation ring of T, and this Q, it acts on everything, and so this is well defined. And the integral form we want is generated basically by the de Mazur divided difference operators, and multiplication by scalars. This is not good at all. I just pulled something out. All right. And okay. Sorry. Help. Yeah, it stays. Murdered the thing. Uh-oh. Uh-oh. Oh. Close call. Okay, so this is the de Mazur operator di. It's 1 minus e to the minus alpha I. Ri is the reflection. And so here I have this denominator here, so I'm allowed to because of this fraction field thingy. And then I have this Wahl group element thingy and some other elements that are in this Q of t thingy. So this is definitely in there. And but the point you need is this acts integrally. These de Mazur operators send this integral ring into itself, and then you define K. Now this is the Nilheke. to be the subring generated by the divide difference operators. Actually, I'm going to use TIs more than DIs, just a slightly different one because for technical reasons, and RFT. So to sort of take the integral scalar, well, they're not really scalars because they're not central, and these divide difference operators. And these are the operators, the good operators that act on the K theory. That's the way that that Peterson views them. Well, at least in the cohomological situation. And it's a fact that there's a commutation relation that allows you to write things this is not commutative, but there's a commutation relation that allows you to put your quote scalars in RFT to the left side. And T sub W is the usual kind of thing where you have TIs defined for simple reflections, and you just define this for a reduced word. And what's the point of this? Yeah?
It says TI equals plus 1. TIH? TI plus 1, right?
TI plus 1, sorry.
I have been confused with it.
Sorry, that's not supposed to be the confusing part. That's supposed to be a simple formula. Yeah.
It's a TI applying to H is 1.
Yeah, sorry. Stop me sooner so I won't go babbling on and you'll be like going, you know. Okay, so this thing has a basis that's over at least RFT that's indexed by, remember this is the Ekman K-theory point that's indexed by the Weil group. Over here we have something indexed by the Weil group. They're the right size, okay? And then you can make a so I'm going to replace this by K, and then make a perfect. And there's a perfect pairing that's sort of RFT linear in the appropriate sense. So I compare. So if A sub W is in Q of T, which it may have to be, because I'm expressing things in terms of Weil group elements, not in terms of the T's. So this may be an integral element, but you can't tell from these kind of coefficients whether it is or not. If I have, now over here, remember these things are functions. These are functions on the Weil group. These are linear combinations, well, of W or T sub W's. And it just define this to be the summation of A sub W, F of W. And so this is perfect sort of RFT or KT of point bilinear. So that's a fact. I'm really just doing linear algebra. I'm not doing anything fancy here. And the cool thing is that the fact, and this is also essentially due to Kostin and Kumar, although they use different bases, is that TW, the TWs, and the functions corresponding to Schubert structure sheaves are dual bases. And I put bases in quotes because on this function side, there's infinite linear combinations allowed. On this side, there's only finite combinations allowed. Okay, so that was just linear algebra. So we shouldn't be too happy yet. Okay, so now we're going to get to an actual statement of some kind of theorem that we did. So it turns out that what we need to do is consider equivariance not for the maximal torus, but for a slightly smaller one in the affine case. So now we're going to go to the affine case. So now we have affine flags, but we're not going to use the big torus, the maximal torus. We're going to use the torus without loop rotation. So we're going to use the T that's inside the G. And this is max inside the G. So this is the one without the loop rotation. And now what we want to ask ourselves, okay, remember that we identified this K-theory by functions on the Weil group that had some divisibility properties. But that was only true for the maximal torus. So this would be like for the T-AF. That's what the theorem would be. I should say that I forgot to give some credit. So that GKM theorem, that divisibility theorem, that condition for being in the image is, I guess the first place is actually written down for K theory is Harada, Holm, and Enrique and Holm, and they do it for the thin end flags, and which is not quite the same space, and they do it for other generalized cohomology theories as well. So our first theorem is sort of a GKM for a small torus in the affine case. And lest you think that we just pulled it out of out of air from our brilliance, what we did is we took an analog in K theory of a different result of GKM. So I'll write GKM2 for a different paper of GKM, not the famous one that people always refer to, but a different one in the homology or cohomology case. They did it. And so what you find in this business is that in K theory, it's not necessarily hard to guess the answer because you know what happens in cohomology, but it's usually harder to prove it, sometimes a lot harder. In this case, it was probably equally hard. I don't know. But that's the way things tend to go. So the statement is in the affine case, this is equal to the following set of functions. So we have the following conditions. Firstly, that 1 minus e to the alpha to the d divides our function. Now I should explain this notation. So I'm not done stating the condition yet, but what you have to do here, so this is the translation element corresponding to the coroot alpha check. You need to do the binomial expansion of this. Then what you get a bunch of stuff multiplied by w. You multiply all that out. You get a scalar linear combination of Weil group elements, and then you just this expression. So we're defining f of summation a sub w, defining this to be the summation of a sub w f of w like this. So you just do the expansion and do that linear expansion, and then I can evaluate these things at these w's. So this is for positive integers d and positive real roots alpha. Those are affine positive roots. And another similar divisibility condition, you get 1 less power d minus first power, and here you put 1 minus r alpha w, and for the same things. So this one, if the d was 1 and this thing was gone, then this would be w versus r alpha w, and it looks exactly like the old condition. But this is what's true for for the small torus for affine flags. And it's kind of mildly interesting. And for the affine Grassmannian, which is there's a standard way to get the same kind of functions for any Kac-Moody Gmod P, like the Kac-Moody flags is like the Kac-Moody Gmod B, but you can do any kind of Gmod P. It's easy to modify these functions to get those, and I'll just write down what you end up getting. It's not trivial if you have the small torus. If you had the maximum torus, there's a standard way of doing everything. So that's not a problem. So this is the set of functions, the affine Val group to our favorite scalar ring, such that 1 holds. So you just get this first condition, and you also need that. And now this is the point that this affine Grassmannian is like a GF. Ger is like GF mod PF, where PF is the max parabolic corresponding to sort of omitting the 0 node. So because of this P here, we have to. There's this invariance condition that you require. So if you change something, so this function has to be constant. It's a function on the whole affine Val group, but it's constant on these cosets. That's what it means to sort of correspond to a class in this Gmod P. So that's the first. W is the finite Val group. WF is the affine Val group. Oh, W is all W in WF. Yeah, sorry. Other questions?
In that one there, the T alpha check is the translation.
Yes.
Can you say what's geometrically happening there? I mean, is there somehow a line from W to
In the alpha check direction or something like that? I haven't thought too much along these lines. Michelle Brown asked me a similar question, but yeah, sorry. This is when it becomes clear I'm not a geometer. I'm just trying to compute something, so I do what I need to do to compute it. There's something going on, and probably McPherson could tell you. Okay. So this is good because it gives me the small torus, which is one of the little ingredients that I needed at the end of the day. And now we need to. So we're in. Now we think that we're in the affine case, and we've got the smaller torus. That's good. Now we need to know what happens over here. So this is the one the cool things happen. There's a couple. So far, I mean, okay, before the small torus bit, it worked in complete Kac-Moody generality. Now, for certain reasons, we need the small torus, so that's a little bit special. But the most cool features, which are special to the affine Grassmannian, are happening now. So there's two bonus features. When in working in the homology or K-homology of the affine Grassmannian, the first one is that there's a multiplication in the homology, or you can think it in the K-homology. So to explain this, let K be the max compact form inside G. G is the semi-simple algebraic group, not the affine thing. It's a finite-dimensional thing, and this is like if G is a SL, this is like SU, and let T sub real be the intersection of the max algebraic torus with this compact form, and then we have some continuous kinds of things to replace the affine Grassmannian and the affine flags with. So we have loop space. So this is just maps from the circle to the group, continuous maps, and base loops, which must send the identity element in this. If you want to think of that as the circle group, then this must send that base point to the identity in the compact group. So those are base loops. And Quillen showed that there's a weak, so there's a torus equivariant weak homotopy equivalence between base loops into the compact and the affine Grassmannian. And what this means, one thing it implies, is that they have the same homology, the same cohomology, equivariant as well. And likewise, well, I don't know who this is due to. It occurs in Peterson writes this down. So this is the affine end flags, not the Kashiwara thick flags, but the thin flags. The end flags are weakly homotopy equivalent equivariantly with LK mod T. And so if you only care about homology, you can forget about the affine Grassmannian and work with base loops. But the brilliant thing about base loops is that you can multiply loops that are going into a group. These are maps into a group. You can multiply them pointwise, and so therefore you get a product structure on. So this would explain the product structure on equivariant homology. Right? I'm really not doing any construction of a equivariant K homology. I'm just getting geometric analogies, and then I'm going to actually do the work algebraically. But I'm explaining why. This explains why. So there's a multiplication, therefore you can expect well, something like this. I haven't defined what I meant by equivariant K homology, so but you can expect some kind of multiplication. That's the point, and you can replace. Then you want to replace this by the algebraic things. So so even though I'm working in the wrong category to be able to write something like that, that's what you should be thinking. That's what I'm secretly doing. Although I'm going to do everything algebraically as to bypass these technical stuff that I don't understand how to do very well. So that's one. So that was bonus feature number one. As you expect a multiplication on this. So let me write down here. So we have here Grassmannian here, some kind of equivariant K homology, some kind of equivariant cohomology, which we already know has the nice ring structure, and a perfect pairing to here. So I've told you what this is, what that is. Now I have to tell you what the ring structure is over here. And I guess I've explained why you should expect a ring structure here. Now, where should you find what this is? Well, I already gave as an algebraic replacement from this the K this Noheke. And so I'm going to use that, or this is Peterson's strategy in the cohomological case, is to use the algebra to build a nice commutative algebra inside of it. So now to do that, you need what I call the wrong way map. So normally, if you had, I'll just write things in the end world. If you had your affine flags to be GF mod BF, and you had your affine Grassmannian to be GF mod PF, and the PF contains the BF, well, then there's clearly going to be a map that you just mod out by a bigger coset and go that way. So in cohomology, you'll get equivariant cohomology, you get contravariant, you'll get map going this way. So and it's just the inclusion of those functions, certain kinds of functions, and the other kinds of functions if you want to work in the function world, which we like to do. But there is a wrong way map, and it's not algebraic. So the wrong way map happens like this. So here we have base loops. They include into all loops, and that projects to all loops mod that real torus. So that's a perfectly good map, composite map there. But remember, we should be thinking that this base loops is Grassmannian, and this other thing is affine flags. Well, hey, that map went the wrong way. This is the map that exists in utter generality, the one you expect to happen. This is the weird one that happens because of some sort of topological category sneakiness. And so indeed, you can define, there is a map. So there is a map. So there's a map from and I should probably be really using sort of the thick version of the Grassmannian here. And what you do is you send a function, f maps to the function which sends, what's the right way to say this? Where is it? So here I have a function like this. How do I make it live in this in this other set? What I do is I send w to f of t lambda, where w and t lambda are in the same coset mod the finite Val group. So this is a weird thing to do, but it works. You make this definition because of knowing these other things. You make this definition and it works. So this is a purely algebraic definition here. This is just using the fact that the affine Val group is the finite one semi-direct product with the coefficients to do that. And you check that this actually defines the class. And this thing is the core. You should think this is the comorphism of this other weird non-algebraic map. But you actually get this map here. And what does this do? Okay, if I dualize this, that tells me that I should get a map. Dualize. So I have a map going that way in cohomology, so I get a map that way in k-homology. So I should get a map like this, going this way. So I'm writing these things as if I have maps. So whenever I have the equivariant k-homology, I don't really define that directly. I just define it as the dual. But this thing, so whatever this gadget is, it should be living inside here and not be a quotient. That's the point. This thing here was the Nilhecke algebra, and there's a important modification you have to make here, that because you're using the affine Val group, but the finite torus, you have to use the level 0 action. Level 0 action of the affine Val group on the finite torus, and use this action to define this Nilhecke. So this is not quite it's a variant of the Kosten-Kumar-Nilhecke, except it's got this smaller torus working, and that is really, really important. That you made that little change. Okay, so you expect this guy to be inside here. And so the theorem, our theorem, is that there's a Hopf isomorphism. Well, I'm going to state it sloppily. I'll say it this way. So what's the image of this? So there's going to be a Hopf isomorphism of this, which is just the dual of the K cohomology, and this, which is the stuff that commutes with the scalars inside the nil-Hecke. And I think I'm running out of time, so I'll just say it fast, is that we can characterize Schubert classes and so we can do the same sort of thing that that Peterson did. We can also, in type A, we can make symmetric functions. Rings of symmetric functions for the Schubert bases. New bases of symmetric functions of non-equivariance. So this is for Ger SLN. And in the case of the K homology, the top degree terms, these are inhomogeneous. The top degree terms are K-Schur functions, which are invented to be triangular with Macdonald polynomials. So that's it.